Welcome back. In this video we will be looking into soft margin support vector machines, the select variable, hyperparameter C, and the optimization problem that comes with it. Let's get started. First, why would we need a soft margin? So in the real world, data is not always linearly separable because it is noisy, has outliers, and just in general, without preprocessing and removal of outliers does not come so that we can just clearly draw a line between them and be done. You can see on the example on the left side, one of the flowers has an outlier which would make it seem like it belongs to the other one, and because of this single outlier we cannot draw a line that would separate these two clearly. In the example on the right side, the outlier does allow us to draw a line, however the line would not be the optimal representation of where the line should be between these two categories, as of course one of them is an outlier, so that does not represent the category, the whole class as a whole. And that is why we need to be cautious about outliers when using SVMs, as they are highly sensitive to them. If there is an instance that is in the gutter or in the street or on the wrong side of the hyperplane, then I will refer to that as a margin violation. So now we will be looking into why we would like to use a soft margin that would allow us for some misclassifications instead of a strict separation. We will introduce now a select variable which is called zeta or z, and the purpose of the select variable is so that we don't have to have all the data correctly assigned on one side or the other side of the hyperplane, but we allow for some slack, so for some errors, misclassifications. The values of the select variable zeta come per one instance, so one data point. If the instance is on the correct side of the hyperplane, then the value for this one data point of zeta is 0. If it is in the gutter, so on the wrong side of the margin, then the value is bigger than 0, and if it's on the completely wrong side of the hyperplane, that is bigger than 1. So altogether, if we're talking about a margin violation, then that means that the value of zeta will be bigger than 0 per each one data point that we are looking at. Now this zeta select variable is connected to hyperparameter C that we are using in our code in scikit. C represents the amount to which the margin can be violated. So zeta tells you how much the slack is, and C tells you how much we can violate the margin. The higher the C, the lower the slack, which means that C would suppress our slack zeta. If the slack is low, that means that we are less tolerant for violations of the margin. So those that are on the wrong side of the hyperplane or those that are in the gutter. We can see on the examples on the two pictures. Let's first look at the left one where C is 1, which is a low value. So because the value of C is low, then the slack is high, which means that we are misclassifying a lot of the instances. You can see that each misclassified instance is marked with red, and a misclassified instance means that the zeta is bigger than 0. So some are in the gutter, which means the value is between 0 and 1, and some are on the wrong side of the hyperplane completely. If we look at the right example, where the C is 100, which is a relatively large value, then we are thriving to classify all the instances correctly, which can lead to the opposite problem of overfitting. In low C, we had the problem of underfitting, and in high C, we have the problem of overfitting. And I hope you can see where this is going, because we need to find a nice common ground, some middle point, where we will not be underfitting or overfitting. And that's what we're gonna look at right now. So the soft margin support vector classifier is the hyperplane solution to the following optimization problem. We are trying to minimize the slack and balance between generalizing the model, so having a larger margin, but minimizing the misclassification errors. If the misclassification errors are too big, then our model does not predict the values correctly. But if we want to predict all of them correctly, then we are risking overfitting. We also have to take into consideration the margin size. So we would like a large margin to allow for some misclassification, but we also want to minimize the amount of instances that end up misclassified. And subject to just means that we need to keep our zeta bigger than 0, because that is the rule. All the values of zeta have to be bigger or equal to 0. And the rest of the mathematical expression just says that we need to ensure that correctly classified points are at least margin 1 away from the hyperplane, which means that they are outside of the gutter on the correct side of the hyperplane. And we are seeing again this W0 plus the dot product of X and W. If you can remember from before, W is the weight vector, X is the input feature vector, and W0 is the bias. And we saw this before when we were looking at the definition of a hyperplane. So when we are talking about soft margin SVM, we are talking about instances that are not linearly separable and require some sort of slack to allow for misclassifications. For example, in case of outliers, then we would like this one single outlier not to throw our entire line to its direction, but to just say, okay, that one will be misclassified and that's okay. However, we also want to keep the misclassification number low while not doing any overfitting or underfitting, and that's why we need to play around with the hyperparameter C. In the last video, we will look at code examples how the hyperparameter C influences the separation between the two classes, so stay tuned for that. But for now, that's it for soft margin support vector machines. I hope you now understand the purpose of the slick variable and its effects on the hyperparameter C. If you have any questions, you can drop them in the comment section, and I'll see you in the next one.